So if we assign the values of x, y, z as 3, 4 and 5, if the statement is valued, if it is true, check whether it is true or false. So the two most important quantifiers are universal quantifiers, that is for all, symbolically we will represent for all, and the existential quantifiers, there exist, that is denoted as like. What is the statement? We have given every real number as an additive inverse is translated as for all x there exists y into x plus y is equal to 0. Hello dear students, welcome to this session of Discrete Mathematics Structure. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. Today in this session, I am going to discuss regarding predicates and quantifiers. So just in your syllabus, you have only the meaning of predicates and the quantifiers, just an introduction to predicates and the quantifiers. Now let us know regarding what is meant by a predicate first. Now let us consider a statement. Let me give an example. Let me write E goes to school. Let us write a statement. Suppose if I take E goes to school, so here there are two parts. E is one part and goes to school is the second part, right? E goes to school. So here E is the first part and the second part is the goes to school. Here the first part is called as the subject. This is the subject and the second part is called as the predicate. So this is called, the second part is called as the predicate. So here the first part is called as the subject and the second part is the predicate. So this predicate is the property of the subject. The property of subject is the predicate here, right? Now let us take an example. Consider the following statements. X is greater than 3, y is equal to x plus 3 and x plus y is equal to z. There are three statements. One is x is greater than 3 and x is equal to y plus 3 and x plus y is equal to z. So here the truth values of these statements has no meaning without assigning the specific values for x, y and z. So without assigning any values for x, y and z, the statement has no meaning. We cannot say whether the given statement is true or false logically. Now let us take this example. If x is greater than 3, let me consider x is greater than 3. So for this x is greater than 3, without assigning any values of x, we cannot judge whether the given statement is true or false. So if I put x is equal to 1, x is equal to 2 and x is equal to 3, I can write 1 is greater than 3, 2 is greater than 3 and 3 is greater than 3. Whether it is true or false. So 1 is greater than 3 is false. I can write F. 2 is greater than 3, that is also false. 3 is greater than 3, that is also false. 3 is equal to 3. So if I assign certain values for these statements, then it will have a meaning. Without assigning any values for this, without specifying, there is no meaning for the given statements. Now, however, we can make the proposition out of such statements. So a predicate is the property that is affirmed or denied about the subject. So the property of the subject is the predicate. Okay, see here in this example, E is nothing but the subject. Goes to the college is the predicate. The property who he goes to the college is the predicate. So a predicate is the property that is affirmed or denied about the truth of the subject. So in logic we say variables are arguments. So here they are nothing but the variables are the arguments of a statement. Now here x is the subject, E is greater than 3 is an predicate, that is greater than E is the predicate. So the terminology is affirmed means holds, E is true, denied does not hold, it is not true. So here affirmed or holds is nothing but true, denied means does not hold, then it is called is not true, that is false. Okay. Now let us come to the exact definition of a mathematical definition in discrete mathematics. How we are going to define the predicate. So that is nothing but, a predicate is nothing but the propositional function. So a statement of the form a statement of the form P of x1, x2, etc. xn is the value of the propositional function P. Here x1, x2, xn is an n tuple and P is called the predicate. So, a statement of the form is the value of the propositional function P is called the predicate. So, here x1, x2, x3 are all xn is an n tuple and this P is called as the predicate. Okay. So, therefore, this predicate is also called a propositional function. This is called propositional function. So, denoted as P of x1, x2, x3, etc. xn, where x1, x2, xn are called n tuples and P is called as the predicate. Now, let us come to a small example. Let me explain with a small example. Let us consider, let Q denotes, Q is x, y, z. So, 3 tuples here denoted the statement as x square plus y square is equal to z square. What is the truth value of Q? 3, 4, 5. What is the truth value of 2, 2, 3? How many values of x, y, z make the predicates true? Now, here let us come to the first statement, Q of 3, 4, 5. Q, what is given condition? X square plus y square is equal to z square. If we assign the values of x, y, z as 3, 4 and 5, if the statement is valued, if it is true, check whether it is true or false. So, since 3 square, put x is equal to 3, 3 square, x is equal to 4, 4 square, 3 square plus 4 square. What is 3 square plus 4 square? 3 square plus 4 square can be done as 9 plus 16, that's equal to 25. On the right hand side, what is the value of z square? Z is equal to 5 square. 5 square is also equal to 25. So, that is 25 is equal to 25. So, therefore, the value Q 3, 4, 5 is true. So, the predicate, this is the given statement is true. Okay. Suppose if we consider the another value, the truth value for this Q 2, 2, 3. So, that is 2 square plus 2 square. 2 square plus 2 square is equal to 4 plus 4 is equal to 8. On the right hand side, what value we have is 3. 3 square. What is 3 square? 3 square is equal to 9. So, this 3 square is 9 is not equal to 8. Therefore, the value Q 2, 2, 3 is false. That means, here the statement x square plus y square is equal to z square is true for the value of Q 3, 4, 5 and it is false for the value of Q 2, 2, 3. Now, how many values of x, y, z make the predicates true? Means there are infinitely many values of x, y, z that makes this proportional function true. This is a small example to explain the concept of this predicate, right? Now, let us come to the next concept here. So, the value of x, y, z, the value of the statement x square plus y square is equal to z square is true only for, this is true for Q of 3, 4 and 5, this is true. Whereas for Q 2, 2, 3, the statement is false. That's it. So, this is the conclusion for this. So, the truth value for this is t and the truth value for this is false. That's it. Okay. So, we can write infinitely many values for x, y, z that makes the proportional function as true. Right. Now, let us come to the next concept, that is a quantifier. What is a quantifier actually? A quantifier is nothing but an operator used to create a proposition. That's it. It is an operator which is used to create in the propositional statement. So, to create a propositional statement, we are going to use an operator. Such an operator is called as a quantifier. Now, a predicate becomes a proposition when we assign it fixed values. Whenever a fixed values are assigned for a predicate, then that predicate will become a proposition. However, another way to make the predicate into a proposition function is to quantify it. So, that is the predicate is true or false for all possible values in the universe of discourse or for some values in the universe of discourse. So, we are going to use an operator. That operator is called as a quantifier. Now, such quantification can be done with two quantifiers, that is universal quantifiers and the existential quantifiers. Now see here, a predicate will become a proposition when we assign it a fixed value. Whenever a fixed values are assigned for a predicate, then it becomes a proposition. However, another way to make the predicate into a proposition is to quantify it. So that is, the predicate is true or false, or for all possible values in the universe of discourse. So, or for some values of s in the universe of discourse. Now, such a quantifiers can be done with two quantifiers. They are nothing but the universal quantifiers. Another one is existential quantifiers. Now, let us come to the definition of quantification. Now, what is the definition? The universal quantification of the predicate P of x. So, if P of x is the predicate, then the universal quantification of the predicate P of x is the proposition P of x is true for all the values of x in the universe of discourse. So, it is true for all the values of x in the universe of discourse. We denote the quantifier as for all x P of x, which can be read it as for all x P of x, for all x P of x. So, this is the usual representation of a quantifier for all x P of x. Now, if the universe of discourse is finite, then say n1, n2, nk, then the universal quantifier is simply the conjunction of all the elements. That is, for all x P of x is P of n1 conjunction, P of n2 conjunction, etc. P of nk. So, if the universe of discourse is finite, if there are finite number of elements, then we say, let us consider n1, n2, etc. nn, n into k, n of k. So, then the universal quantifier is simply the conjunction of all the elements, that is denoted as for all x P of x. That is, universal quantifier is equal to P of n1 conjunction, P of n2 conjunction, P of n3, etc. P of nk conjunction, P of nk. This is how we are going to represent the universal quantifier. Now, let us come to the next concept, predicate of logic. Predicate logic. Now, a predicate, a predicate P of x is a declarative sentence if it depends on, if the value depends on, that means whose truth values depends on one or more variables. If the truth values depends on one or more than one variable, then a predicate P of x is declarative sentence. So, a predicate P of x is a declarative sentence whose truth values depends on more than one or more variables. Now, let us consider if P of x is also said to be the value of the propositional function P at x, then P of x becomes a propositional when a variable x is assigned to it from the domain of U, Now, in quantifiers, we need to quantifiers to express the meaning of English words including all and some. Say, let us consider, for example, all students in the class are computer science majors. All the students in the class are computer science major students. So, the quantifiers we need to express the quantifiers in meaning of English words including all and some. Here we have included all. All the students in this class are computer science majors. There is a math major student in this class. So, the two most important quantifiers are universal quantifiers, that is for all, symbolically we will represent for all, and the existential quantifiers, there exist, that is denoted as like this. So, most important quantifiers are for all and there exist. These are the two quantifiers which we are using to solve the problems in this mathematical logic. That is, the two important quantifiers are universal quantifiers, that is denoted as for all, the symbolic representation is for all, and existential quantifier, there exists, existential quantifier, that is nothing but there exists, which is symbolically denoted as there exists and for all. These are the two important quantifiers. Now, let us take few notations. We write as the quantifiers as in for all x p of x and there exists x p of x and p of x. See, so we write the quantifiers as in for all x p of x and there exists x p of x. So for all x p of x is asserts p of x is true for every value of x in the domain. So here for all x, this p of x will asserts p of x is true for every value of x. For all the value of x, this p of x will asserts whether it is true for every value in its domain. Suppose if x1, x2, xn, then for all x, p of x can be written as p of x1 conjunction p of x2, etc. conjunction p of x1. Now, there exists x p of x assert p of x is true for some x in the domain. So, that is denoted as if x is equal to x1, x2, etc. xn, then there exists x and p of x is equal to p of x1 disjunction p of x2, etc. disjunction p of x1. So, here for all x p of x is denoted as p of x1 conjunction p of x2, etc. conjunction p of x1. Whereas for there exists x, p of x asserts the true for some values of x in the domain is denoted as there exists x such that p of x is equal to p of x1 disjunction p of x2, etc. disjunction p of x1. So, one is the conjunction, another one is the disjunction, right. Now, let us come to the next concept, that is nested quantifiers. Nested quantifiers. Nested quantifiers are often necessary to express the meaning of the sentence in English as well as an important concept in computer science as well as in mathematics. To get the proper meaning in English grammar as well as in computer science language as well as in mathematics, so the nested quantifiers are often necessary to express the meaning of the sentences in English as well as important concept in computer science as well as in mathematics. So let us consider, for example, every real number has an additive inverse is translated as for all x there exists y into x plus y is equal to 0. Every real number has additive inverse. Every real number has additive inverse is translated as for all x there exists y into x plus y is equal to 0. Here, what is the statement we have given? Every real number has an additive inverse is translated as for all x there exists y into x plus y is equal to 0, where the domain of x and y are the real numbers, right. Here the domain of x and y are the real numbers. Similarly, so to translate English the statement for all x and y, for all x, for all y, if x is less than 0, conjunction, that is and if x is less than 0 and y is less than 0 implies xy is greater than 0, that is for all xy, x for all x, for all y, x is less than 0 and y is less than 0 implies xy is greater than 0, where the domain of x and y are the real numbers. This is how we are going to represent the nested quantifiers. So, here these nested quantifiers are often necessary to express the statements in computers as well as in mathematical. The concepts of mathematical statement can be expressed as the nested quantifiers, like for all x, for all y, for all x there exists, for all x there exists y into x plus y is equal to 0, for all y. Here also the second statement is like this, for all x there exists y into x plus y, for all x there exists y such that x is less than 0, conjunction y is less than 0 implies x and y is greater than 0. Okay, this is how we are going to represent the mathematical statement in the nested quantifiers. These are some basic meaning, definition and the representation of predicates and the quantifiers. So just this is an introduction for the definition of a predicate and the representation, as well as the definition of a quantifier and how we are going to represent the quantifiers. So that's all regarding this basic concept of a predicate and the quantifiers. So in the next section, I am going to take the problems based on the predicate and the quantifiers. The problems based on this predicate and the quantifier, that is very important concept for the point of examination. Don't miss the class, attend the class. That's all regarding today's session. Thank you very much.